Okay, happy Halloween. What I want to do today is share with you advice for applying machine learning. And you've heard me allude to this before, but yeah, I think over the last several weeks, you've learned a lot about the mechanics of how to build different learning algorithms, everything from linear regression, logistic regression, SVMs, random forests, neural networks. And what I want to do today is share with you some principles for helping you become efficient at how you apply all of these things to solve whatever application problem you might want to work on. And so a lot of today's material is actually not that mathematical. But there's also some of the hardest material in this work in this class to understand. It turns out that when you give advice on how to apply a learning algorithm, such as, don't waste lots of time collecting data unless you have confidence it's useful to actually spend all that time. It turns out when I say things like that, people, it's easy to agree. It's like, of course, you shouldn't waste time collecting lots of data unless you have some confidence it's actually good use of your time. That's like a very easy thing to agree with. But the hard thing is when you go home today and you're actually working on your class project, right? To apply the principles we talked about today, when you're actually on the ground talking to your teammates, saying, all right, do we collect more data for our class project now or not? To make the right judgment call for that, to map the concepts you learned today to when you're actually in the hot seat, making a decision. Do we go and spend another 2 days scraping data off the internet, or do we go and tune this parameters algorithm? To actually make those decisions is actually, it often takes a lot of careful thinking to make the mapping from the principles we talked about today, and that probably all of you go, yep, that makes sense. But to actually do that when you're in the hot seat making the decisions, that's something that will often take some careful thought, I guess. And I think, for a long time, parts of machine learning have been an art, right? Where we'll go to these people that have been doing it for 30 years and we say, hey, my learning algorithm doesn't work. What do we do now? And then they would have some judgment, or people would ask me, and for some reason, because we've done it for a long time, we'll say, oh yeah, get more data, or tune that parameter, or try a neural network with big hidden units. And for some reason, it'll work. And what I hope to do today is turn that black magic, that art into much more of a science, so that you can much more systematically make these decisions yourself, rather than talk to someone that's done this for 30 years, then for some reason is able to give you the good recommendations, even if, but turn it from more of a black art into more of a systematic engineering discipline. And just one note, some of what I'm going to do today is not the best approach for developing novel machine learning research. If your main goal is to write research papers, some of what I'll say will apply, some of what I say will not apply, but I'll come back to that later. But so most of today is focused on how to help you build stuff that works, right? To build applications that work. So the three key ideas you see today are: first is diagnostics for debugging learning algorithms. One thing you might not know, or actually if you're working on a class project, maybe you know this already, is that when you implement a learning algorithm for the first time, it almost never works, right? At least not the first time. And so, what is it? I still remember there was a weekend about a year ago where I implemented softmax regression on my laptop, and it worked the first time. And even to this day, I still remember that feeling of surprise, like, no, there's got to be a bug. And I went in to try to find a bug, and there wasn't a bug, but it's so rare. The learning algorithm works the first time. I still remember it like, over a year later. And so a lot of the workflow of developing learning algorithms, it actually feels like a debugging workflow. Right? And so we want to help you become systematic at that. Two key ideas here about our error analysis and ablative analysis. So how to analyze the errors of your learning algorithm, and also how to understand what's not working with error analysis, and how to understand what's working, which is ablative analysis. And then finally, some philosophies on how to get started on a machine learning project, such as your class project. Okay? So let's start with discussing debugging learning algorithms. So what happens all the time is you have an idea for a machine learning application. you implement something, and then it won't work as well as you hoped. And the key question is, what do you do next, right? When I work on a machine learning algorithm, that's actually most of my workflow. We usually have something implemented, it's just not working that well, and your ability to decide what to do next has a huge impact on your efficiency. I think when I was an undergrad at Carnegie Mellon University, I had a friend that would debug their code by, they write a piece of code, and then, as always, when you write a piece of code, initially always there's a bunch of syntax errors, right? And so their debugging strategy was to delete every single line of code that generated a syntax error, because it was a good way to get rid of syntax. So that wasn't a good strategy. So in machine learning as well, there are good and less good debugging strategies. Right. So let's start with a motivating example. Let's say you're building an anti-spam classifier, and let's say you've carefully chosen a small set of 100 words to use as features. So instead of using 10,000 or 50,000 words, you've chosen 100 words that you think could be most relevant to anti-spam. And let's say you start off implementing logistic with regularization. I think when talked about this, there's also, there's a frequentist in the Bayesian school, but you can think of this as Bayesian logistic regression, where you have the maximum likelihood term on the left, and then that second term is the regularization term, right? So that's Bayesian logistic regression if you're Bayesian, or logistic regression with regularization if you're using frequentist statistics. And let's say that logistic regression with regularization, or Bayesian logistic regression, it gets 20% test error, which is unacceptably high, right? You're making 1 in 5 mistakes on your spam filter. And so what do you do next? Now, for this scenario, I want to, when you implement an algorithm like this, what many teams will do is try improving the algorithm in different ways. So what many teams will do is say, oh yeah, I remember, well, we like big data. More data always helps. So let's get some more data and hope that solves the problem. So some teams will say, let's get more training examples. And it's actually true. More data pretty much never hurts. It almost always helps. But the key question is how much. Or you could try using a smaller set of features. If 100 features, probably some weren't that relevant, so let's get rid of some features. Or you could try adding a larger set of features. 100 features, that seems small, right? So let's add more features. Or you might want other designs of the features. Instead of just using features in the email body, you can use features from the email header. The email header has not just a from to subject, but also routing information about what's the set of servers of the internet that the email took to get to you. Or you could try running gradient descent for more iterations. That never hurts, right? Usually. Instead of gradient descent, let's switch to Newton's method. Or let's try a different value for lambda. Or we say, forget about Bayesian logistic regression or logistic regression regularization. Let's use a totally different algorithm, like an SVM or a neural network or something, right? So what happens in a lot of teams is someone will pick one of these ideas, kind of at random. It depends on what they happen to read the night before, right, about something, or their experience on the last project. And sometimes sometimes you or project leader will say, we'll pick one of these and just say, let's try that, and then spend a few days or a few weeks trying that, and it may or may not be the best thing to do. So I think that in my team's machine learning workflow, so first, if you and a few others sit down and brainstorm a list of the things you could try, you're actually already ahead of a lot of teams, because a lot of teams will kind of just by gut feeling, right, or the most opinionated person will pick one of these things at random and do that. But if you brainstorm a list of things and then try to evaluate the different options, you're already ahead of many teams. And I think I think right, unless you analyze these different options, it's hard to know which of these is actually the best options, right? So the most common diagnostic I end up using in developing learning algorithms is a bias versus variance diagnostic, right? And I think talked about bias and variance already. If a classifier is highly biased, then it tends to underfit the data. So high bias is, well, actually, you guys remember this, right? If you have a data set that's like this, a highly biased classifier may be much too simple, and high variance classifiers may be much too complex, and something in between, would trade off bias and variance in an appropriate way, right? So those bias and variance. And so it turns out that one of the most common diagnostics I end up using in pretty much every single machine learning project is a bias versus variance diagnostic to understand how much of your learning algorithms problem comes from bias and how much of it comes from variance. I've had, I don't know, like former PhD students, right, that learned about bias and variance when they're doing their PhD, and then sometimes even a couple of years after they graduated from Stanford and worked, on more practical problems, they actually tell me that their understanding of bias and variance has continued to deepen, right, for many years. So this is one of those concepts is if you can systematically apply it, it'll make you much more efficient. And this is really maybe the single most useful tool I've found, understanding bias and variance and debugging learning algorithms. And so what I'm going to describe is a workflow where you would run some diagnostics to figure out what is the problem, and then try to fix what the problem is. And so just to summarize this example, linear regression error is unacceptably high, and you suspect problems either high variance or high bias. And so it turns out that there's a diagnostic that lets you look at your algorithm's performance and try to figure out if how much of the problem is variance and how much of the problem is bias. Oh, and I'm going to say test error, but if you're developing, should I really be doing this with a dev set or a development set rather than a test set, right? But so let me explain this diagnostic in greater detail. So it turns out that if you have a classifier with very high variance, then the performance on the test set, or actually, better practice to use the holdout cross validations of the development set, you see that the error that you classify has a much lower error on the training set than on the development set. But in contrast, if you have high bias, then the training error and the test set error on the dev set error will both be high. So let me illustrate this with a picture. So this is a learning curve, and what that means is on the horizontal axis, you're going to vary the number of training examples, right? And when I talked about bias and variance, I had a plot where the horizontal axis was the degree of polynomial, right? For the first order, second order, third order, fourth order polynomial. In this plot, the horizontal axis is different, it's number of training examples. And so it turns out that whenever you train a learning algorithm, the more data you have, usually the better your development set error, the better your test set error, right? It's just error usually goes down when you increase the number of training examples. The other thing, and let's say that you're hoping to achieve a certain level of desired performance. For business reasons, you like your spam classifier to achieve a certain level of desired performance. And sometimes desired level of performance is to do about as well as a human can. That's a common business objective depending on your application, but sometimes it can be different, right? So you have your product manager, tells you that, or if you're leading the product, you think that you need to hit a certain level of target performance in order for this to be very useful spam filter. So the other plot to add to this, which will help you analyze bias versus variance, is to plot the training error. Now, one interesting property of training error is that it increases as the training set size increases. Because if you have only one example, right? Let's say you're building a spam classifier, and you have only one training example, then any algorithm, can fit one training example perfectly. And so if your training set size is very small, the training set error is usually 0, right? Because if you have like 5 training examples, probably you can fit all 5 examples perfectly. And it's only if you have a bigger training set that it becomes harder for the learning algorithm to fit your training data that well, right? Or in the linear regression case, yeah, if you have one example, yeah, you can fit a straight line to the data. If you have two examples, you can fit any model pretty much to the data and have zero training error. It's only if you have a very large training set that a classifier like logistic regression or linear regression may have a harder time fitting all of your training examples. So that's why training error or average training error, average over your training set, generally increases as you increase the training set size. So now, there are two characteristics of this plot that suggest that if you plot the learning curves, if you see this pattern, this suggests that the algorithm has a large bias problem, right? And the two properties written at the bottom, one, the weaker signal, the one that's harder to rely on, is that the development set error or the test set error is still decreasing as you increase the training set size. So the green curve is still, still looks like it's going down. And so this suggests that if you increase the training set size and extrapolate further to the right, that the curve would keep on going down. This turns out to be a weaker signal because sometimes when you look at the curve like that, it's actually quite hard to tell, to extrapolate to the right. If you double the training set size, how much further would the green curve go down? It's actually kind of hard to tell. So I find this a useful signal, but sometimes it's a bit hard to judge, exactly where the curve will go if you extrapolate to the right. The stronger signal is actually the second one. The fact that there's a huge gap between your training error and your test set error, or your training error and your dev set error would be a better thing to look at, is actually a stronger signal that this particular learning algorithm has high variance, right? Because as you increase the training set size, you find that the gap between train and test error usually closes, usually reduces, and so there's still a lot of room for making your test set error become closer to your training error. And so if you see a learning curve like this, is a strong sign that you have a variance problem. Okay, now let's look at what the learning curve will look like if you have a bias problem. So this is a typical learning curve for high bias, which is that's your dev set error or your development set, the whole cross validation set error, test set error, and you're hoping to hit a level of performance like that, and your training error looks like that, right? And so one sign that you have a high bias problem is that this algorithm is not even doing that well on the training set, right? Even on the training set, you're not achieving your desired level of performance. And it's like, look, imagine you're looking at learning algorithms, it's like this algorithm has seen these examples, and even if examples are seen, it's not doing as well as you were hoping. So clearly the algorithm's not fitting the data well enough. So this is a sign that you have a high bias problem, not enough features, your learning algorithm is too simple. And the other signal is that there's a very small gap between the training and the test error, right? And you can imagine when you see a plot like this, no matter how much more data you get, right? Go ahead and extrapolate to the right as far as you want. No matter how much more data you get, no matter how far you extrapolate to the right of this plot, the blue curve, the training error, is never going to come back down to hit the desired level of performance. And because the test set error is generally higher than your training set error, no matter how much more data you have, no matter how far you extrapolate to the right, the error is never going to come down to your desired level of performance. So if you get a training error and test set error curve that looks like this, you kind of know that while getting more training data may help, right? The green curve could come down like a little bit if you get more training data. The act of getting more training data by itself will never get you to where you want to go. Okay. So let's work through this example. So for each of the 4 bullets here, each of the first four ideas fixes either a high variance or high bias problem. Right? So let's go through them and ask for the first one. Do you think it helps you fix high bias or high variance? High variance, right? Okay, wait, cool. All right, high variance, right? Anyone want to say, well, right? Anyone want to say why? Yeah, go ahead.
It might be harder to like match all of the data points and therefore have really high overfitting if you have a lot of data.
Right, cool. Yes, right, yeah, right. I guess if you're fitting a very high order polynomial that wiggles like this, if you have more data, it will make it, then it won't at least oscillate so crazily even if you fit a high order polynomial, right? And if you look at the high variance curve, wow, there's a lot of latency in my laptop for some reason. Huh. Right? So this is a high variance plot. And if you have a learning algorithm of high variance, you can hopefully, if you extrapolate to the right, there is some hope that the green curve will keep on coming down. So getting more training data, if you have high variance, which is if you're in this situation, it looks like it could have your hope. It's worth trying, right? Can't guarantee it'll work, but it's worth trying.
Do we know anything about these functions, like for certain algorithms that are for like sampling uniformly to the distribution?
Oh, I see. Yes, sorry. This is a good point. So let's see. The curves will look like this, assuming that your training data is IID, right? Training and depth and test sets are all drawn from the same distribution. There is learning theory that suggests that in most cases, the green curve should decay as 1 over square root of m. That's the rate at which it should decay until it reaches some Bayes error. That's what the learning theory says. Does that make sense? And sometimes, and learning algorithms errors don't always go to 0, right? Because sometimes, sometimes the data is just ambiguous. I don't know, like I guess my PhD students, including on them, we do a lot of work on healthcare, and sometimes you look at an X-ray, it's just blurry, and you could try to make a diagnosis, right? Is there or Anand's working on predicting patients' mortality, right? What's the chance of someone dying in the next year or so? And sometimes you look at a patient's medical record and you just can't tell, right? What is, will they pass away in the next year or so? Or you look at an X-ray, you just can't tell, is there a tumor or not, because it's just blurry. So learning algorithms error don't always decay to 0, but the theory says that as m increases, it should decay at roughly a rate of 1 over square root of m toward that baseline error, which is called Bayes error, which is the best that you could possibly hope anything could do given how blurry the images are, given how noisy the data is, right? All right. Oh, sorry, I gave the answer away. Okay. So try a small set of features that fixes a high variance problem, right? And one concrete example would be if you have this data set and you're fitting a 10th order polynomial and the curve oscillates all over the place, that's high variance. You could say, well, maybe I don't need a 10th order polynomial. Maybe I should use only, oh, wow, I don't know what sorry, what's going on? That's weird. Okay, right, so maybe you say, maybe I don't need my features to be all of these things, 10th order polynomial. Maybe if this is too high variance, I'm gonna get rid of a lot of features and just use much smaller number of features, right? So that fixes high variance. And then if you use a larger set of features, fixes high bias, right? Cool, right? So that's if you're fitting a straight line to the data and it's not doing that well, and you go, gee, maybe I should add a quadratic term and just add more features, right? So that fixes bias. And adding email header features. Bias, right? Yeah, cool. Yep. Generally, I would try this if, to try to reduce bias, right? And so in the workflow of how you develop a learning algorithm, I would recommend that so one of the things about building learning algorithms is that for a new application problem, it's difficult to know in advance if you're going to run into high bias or high variance problem, right? It is actually very difficult to know in advance what's going to go wrong with your learning algorithm. And so the advice I tend to give is if you work on a new application, implement a quick and dirty learning algorithm, have like a quick and dirty implementation of something so you can run your learning algorithm, just start with logistic regression, right? Or start with something simple, and then run this bias variance type of analysis to see sort of what went wrong, and then use that to decide what to do next. Do you go to a more complex algorithm? Do you try adding more data? The one exception to this is if you're working on a domain in which you have a lot of experience, right? So for example, I've done a lot of work on speech recognition, so because I've done that work, I kind of have a sense of how much data is needed for a new application, then I might just build something more complicated from the get-go. Or if you're working on, say, face recognition, and because you've read a lot of research papers, you have a sense of how much data is needed, then maybe it's worth trying something because you're building on a body of knowledge. But if you work on something, on a brand new application that you and maybe no one in the published academic literature has worked on, or if you don't totally trust the published results to be representative of your problem, then I would usually recommend that you build a quick and dirty implementation, look at the bias and variance of the algorithm, and then use that to better decide what to try next. Right? So I think bias and variance is really like the single most powerful tool I know, for analyzing the performance of learning algorithms. And I do this pretty much in every single machine learning application. There's one other pattern that I see quite often, which is which adds just a second set, which is your optimization algorithm working. So let me explain this with an example, right? So it turns out that when you implement a learning algorithm, you often have a few guesses for what's wrong, and if you can systematically test if that hypothesis is right before you spend a lot of work to try to fix it, then you can be much more efficient. So let's explain that with a concrete example so you understand those words I just said. Maybe they're a little bit abstract, which is, let's say that you tune your logistic regression algorithm for a while, and let's say logistic regression gets 2% error on spam email and 2% error on non-spam, right? And it's okay to have 2% error on spam email, maybe, right? So you have to read a little bit of spam email. It's like, that's okay. But 2% error on non-spam is just not really acceptable because you're losing 1 in 50 important emails. And let's say that your teammate, right, also trains an SVM, and they find that an SVM using a linear kernel gets 10% error on spam, but 0.01% error on non-spam. Right? And maybe not great, but for purposes of illustration, let's say this is acceptable. But because it turns out logistic regression is more computationally efficient and it may be easier to update, right? You get more examples, run a few more iterations of gradient descent. And let's say you want to ship a logistic regression implementation rather than SVM implementation. So what do you do next? It turns out that one common question you have when training your learning algorithm is you often wonder, is your optimization algorithm converging, right? So, is gradient descent, is it converging? And so one thing you might do is draw a plot of the training optimization objective of J of theta, or whatever you're maximizing, or log likelihood of J of theta or whatever, versus the number of iterations. And often the plot will look like that, right? And the curve is kind of going up, but not that fast. And if you train it twice as long, or even 10 times as long, will that help, right? And again, training the algorithm for more iterations, it pretty much never hurts. If you regularize the algorithm properly, training the algorithm longer, almost always helps, right? Pretty much never hurts. But is the right thing to do to go and burn another 48 hours of CPU or GPU cycles to just train this thing longer and to hope it works better, right? Maybe not. So is there a systematic way to tell? Is there a better way to tell if you should invest a lot more time in running the optimization algorithm. Sometimes it's just hard to tell, right? So now the other question that you sometimes wonder, so a lot of this iteration of debugging learning algorithms is looking at what your learning algorithm is doing and just asking yourself, what are my guesses for what could be wrong? And maybe one of your guesses is, well, maybe you're optimizing the wrong cost function, right? So here's what I mean. What you care about is this weighted accuracy criteria, where it's sort of sum over your dev set or test set of weights on different examples of whether it gets it right, where the weights are higher for non-spam than spam, because you really want to make sure you label non-spam email correctly, right? So maybe that's the weight accuracy criteria you care about. But for logistic regression, you're maximizing this cost function, right? Log likelihood minus this regularization term. So you're optimizing J of theta when what you actually care about is A of theta. So maybe you're optimizing the wrong cost function. And one way to change the cost function would be to fiddle with the parameter lambda, right? That's one way to change the definition of J of theta. Another way to change J of theta is to just totally change the cost function you're maximizing, like change it to the SVM objective, right? And then part of that also means choosing the appropriate value for C, okay? And so there's a second diagnostic which I end up using, which can help you tell is the problem your optimization algorithm, in other words, is gradient ascent not converging, or is the problem that you're just optimizing the wrong function, right? And we'll see two examples of this today. So this is the first example, okay? And so here's a diagnostic that can help you figure that out. So just to summarize this scenario, this example, this running example we're using, the SVM outperforms the regression, but you want to deploy this regression. Let's set theta SVM, but the parameters learned by an SVM. And instead of writing the SVM parameters as W and B, I'm just going to write the linear SVM with linear kernel, using the logistic regression parameterization, right? So you have like a linear set of parameters. And let's let theta BRR be the parameters learned by logistic regression, right? So just regularized logistic regression or Bayesian logistic regression. So you care about weighted accuracy and the SVM outperforms Bayesian logistic regression. Okay, so this is a one-slide summary of where we are in this example. So how can you tell if the problem is your optimization algorithm, meaning that you need to run gradient ascent longer to actually maximize J of theta, or is, and this is what BLR tries to maximize, right? So how do you tell? We have two possible hypotheses we want to distinguish between. One is that the learning algorithm is not actually finding the value of theta that maximizes J of theta. Right? For some reason, gradient ascent is not converging. So that would be a problem with the optimization algorithm. That J of theta, for the problem to be with the optimization algorithm means that if only we could have an algorithm that maximizes J of theta, we would do great. But for some reason, gradient ascent isn't doing well. That's one hypothesis. The second hypothesis is that J of theta is just a wrong function to be optimizing. It's just a bad choice of cost function. That J of theta is too different from A of theta, that maximizing J of theta doesn't give you, a classifier that does well on A of theta, which is what you actually care about. Okay? So this is a problem setup. Any I want to make sure people understand this. Raise your hand if this makes sense. Most people? Okay, cool. All right, almost right. Okay, good. Any questions about this problem setup? Oh, thank you. Why not maximize A of theta directly? Because A of theta is non-differentiable, so we don't actually have, there's this indicator function, so we actually don't, it turns out maximizing A of theta explicitly is NP hard, but we just don't have great algorithms to try to do that. Yeah. Okay, so it turns out there's a diagnostic you could use to distinguish between these two different problems. And here's the diagnostic, which is take the cost function that logistic regression is trying to maximize, so J, and compute that cost function on the parameters found by the SVM, and compute that cost function on the parameters found by Bayesian logistic regression, and just see which value is higher, okay? So there are two cases. Either this is greater or this is less than or equal to, right? They're just two possible cases. So what I'm going to do is go over case 1 and case 2 corresponding to is greater than or is less than or equal than, and let's see what that implies. So on the next slide, I'm going to copy over this equation, right? That's just a fact that the SVM does better than Bayesian logistic regression on our problem. So on the next slide, I'm going to copy over this first equation, and then we're going to consider these two cases separately. So greater than would be case 1, and less than or equal to would be case 2. Okay? So let me copy over these two equations in the next slide. Right? So that's the first equation that I just copied over here, and this is the greater than is case 1. Okay? So let's see how to interpret this. In case 1, J of theta SVM is greater than J of theta BLR, right? Meaning that whatever the SVM was doing, it found a value for theta, which we've written as theta SVM. And theta SVM has a higher value on the cost function J than theta BLR. But Bayesian logistic regression was trying to maximize J of theta, right? I mean, Bayesian logistic regression is just using gradient descent to try to maximize J of theta. And so under case 1, this shows that whatever the SVM was doing, whatever your buddy implementing SVM did, they managed to find a value for theta that actually achieves a higher value of J of theta than your implementation of Bayesian logistic regression. So this means that theta BLR fails to maximize the cost function J, and the problem is with the optimization algorithm. Okay, so that's case 1. Case 2, again, I'm just copying over the first equation, right? Because this is just part of our analysis. This is part of the problem setup. And case 2 is now the second line is now a less than or equal sign. Okay, so let's see how to interpret this. So if you look at the second equation, right, the less than or equal to sign, it looks like J did a better job than the SVM maximizing J, it looks like Bayesian logistic regression did a better job than the SVM maximizing J of theta, right? So, you tell Bayesian logistic regression to maximize J of theta, and by golly, it found a value of theta, it found a value that achieves a higher value of J of theta than whatever your buddy did using an SVM implementation. So it actually did a good job trying to find the value of theta that drives up J of theta as much as possible. But if you look at these two equations in combination, what we have is that the SVM does worse on the cost function J, but it does better on the thing you actually care about, A of theta. So what these two equations in combination tell you is that having the best value, the highest value for J of theta, does not correspond to having the best possible value for A of theta. So it tells you that maximizing J of theta doesn't mean you're doing a good job on A of theta, and therefore maybe J of theta is not such a good thing to be maximizing, because maximizing it doesn't actually give you the result you ultimately care about. So under case 2, you can be convinced that J of theta is not the best function to be maximizing, because getting a high value of J of theta doesn't get you a high value for what you actually care about. And so the problem is with the objective function of the maximization problem, and maybe we should just find a different function to maximize. Okay? So, any questions about this? Yeah, go ahead.
change do we need fiddle with parameters such as lambda, or find something completely different?
Yeah, let me come back to that. Yeah, it's a complicated answer. Yeah. All right, actually, let's do this first. So, all right, for these 4 bullets, does it fix the optimization algorithm or does it fix the optimization objective? First one, does it fix the optimization algorithm or does it fix the optimization objective? Cool. Second one? Oh, I don't know what's wrong with this thing. This is so strange. Okay, all right. Does it fix the optimization algorithm or fix the optimization objective? Optimization algorithm, right? So Newton's method still looks at the same cost function j of theta, but in some cases, it just optimizes it much more efficiently. This is a funny one. Usually you fiddle with lambda to trade off bias and variance things, right? But this is one way to change the optimization objective. Although usually you change lambda to adjust bias and variance rather than this, right? And then trying to use an SVM, right, would be one way to totally change the optimization objective. Okay. To answer the question just now, sometimes when you find you have the wrong optimization objective, is that there isn't always an obvious thing to do, right? Sometimes you have to brainstorm a few ideas. There isn't always one obvious thing to try, but at least it tells you that that category of things of trying out different optimization objectives is worth your while, right? All right. So let's go through a more complex example. They'll incorporate some of these. Wow, I don't know what's wrong. It's probably my laptop. I wonder if this is so strange. Let me see what I can do. All right, well, all right. Let's go for a more complex example that will illustrate some of these concepts that we've been going through and just let you see another example of these things. And I find that one thing I've learned as a teacher, one of the ways for you to become good at this, right, is to go, work in a good AI group for 5 years, right? Because when you work in a good AI group for several years, then you have seen, 10 projects, and that lets you gain that experience. But it turns out that it takes, I don't know, depending on what AI group you work on, it takes, if you work on a different project every year, then in 5 years, I guess you're working on 5 projects or something. I actually don't know, or maybe 10 projects or something. But one of the reasons that in the way I try to explain these to you, I'm trying to go give specific scenarios with you, is so that, my PhD students and I, we spent like many years working on Stanford autonomous helicopter, but I'm trying to distill the key lessons down for you so that you don't need to work on a project for 3 years to gain this experience, but to give you some approximation to this knowledge in maybe 20 minutes, right? And the 20 minutes won't give you the depth of the 3 years of experience, but at least try to summarize the key lessons so that you can learn from experience that others took years to develop. All right, so this helicopter actually sits in my office, but if you go to my office and grab this helicopter, and we ask you to write a piece of code to make this fly by itself, use a learning algorithm to make this fly by itself, how do you go about doing so? So it turns out a good way to make a helicopter fly by itself is to do the following. Step 1 is build a computer simulator for a helicopter. So, that's actually a simulator, right? Like a video game simulator of a helicopter. The advantage of using, say a video game simulator helicopter is you could try a lot of things, crash a lot in simulation, which is cheap, whereas crashing a helicopter in real life is slightly dangerous and also more expensive. But so step 1, build a simulator helicopter. Step 2, choose a cost function. And for today, I'm just using a relatively simple cost function, which is squared error. So you want the helicopter to fly the position x desired, and your helicopter instead, wanders off to some other place x. So let's use a squared error to penalize it, right? When we talk about reinforcement learning toward the end of this quarter, we'll actually go through the same example again, but using the reinforcement learning terminology, understand this at even slightly deeper level. And we'll go over this exact same example after you learned about reinforcement learning, but we'll just go over a slightly simplified, very slightly simplified version today. And so running reinforcement learning algorithm, and what a reinforcement learning algorithm does is it tries to minimize that cost function j of theta. And so, and so you learn some set of parameters, theta subscript RL, for controlling the helicopter, right? And when we talk about reinforcement learning, you see all this redone with proper reinforcement learning notation, where j is a reward function, theta RL is a control policy, and so on. But don't worry about that for now. So let's say you do this, and the resulting controller, right, the way you fly the helicopter, it gives much worse performance than your human pilot. So the helicopter wobbles all over the place and then doesn't quite stay where you were hoping it will. So what do you do next, right? Well, here are some options corresponding to the 3 steps above. You could work on improving your simulator. It turns out, even today, we've had helicopters for, I don't know, like I think we started having a lot of commercial helicopters around the 1950s, is it? We've had helicopters for many decades now. But airflow around the helicopter is very complicated, and even today, there are actually some details of how air flows around the helicopter that the aerodynamics textbook, that even aeroastro people, right, the experts in aeroastro cannot fully explain. So helicopters are incredibly complicated, and there's almost unlimited headroom for building better and more accurate simulators of helicopter. So maybe you want to do that. Or maybe you think the cost function is messed up. Maybe a squared error isn't the best metric. Right, and it turns out, the way the helicopter has a tail rotor that blows wind to one side, right? So I guess because the main rotor spins in one direction, if it only had a main rotor, then the body would spin in the opposite direction, kind of equal and opposite reaction, but in torque, right? So the main rotor spins in one direction. If it only had a main rotor, the rotor on top, and it just spun that, then the body of the helicopter spin in the opposite direction. So that's why you need a tail rotor to blow air down off to one side to not make it spin the opposite direction. But because of that, it turns out a helicopter staying in place is actually tilted slightly to a side because the tail rotor blows air in one direction, so it's pushing you off to one side. So you have to tilt your helicopter in the opposite direction. So the main rotor blows air to one side, the tail rotor blows air to the other side, so you actually stay in place, right? So helicopter is actually asymmetric. Left and right is not the same. So because of this complication, maybe squared error isn't the best error because your orientation, your optimal orientation is actually not 0, right? So maybe you should modify the cost function, or maybe you want to modify the reinforcement learning algorithm because you secretly suspect that your algorithm is not doing a great job of minimizing that cost function, right? That is not actually finding the value of theta that absolutely minimizes j of theta. So it turns out that each one of these topics can easily be a PhD thesis, right? You could definitely work for 6 years on any one of these topics. And the problem is, so I actually know someone that wrote a PhD thesis on, right, improving helicopter simulator, right? But the problem is maybe your helicopter simulator is good enough, and you can spend 6 years improving your helicopter simulator, but will that actually get you the result? And you can write a PhD thesis and get a PhD doing that, maybe. But if your goal is not just to write a PhD thesis, it's actually make your helicopter fly better. It's actually not totally clear, right, if that's the key thing for you to spend time on. So what I'd like to do is describe to you a set of diagnostics that allows you to use this sort of logical step-by-step reasoning to debug which of these 3 things is what you should actually be spending time on, right? So is it possible for us to come up with a debugging process to logically reason so as to select one of these things to work on and have conviction and be relatively confident that this is a useful thing to work on, right? So here's how we're going to do it. So just to summarize the scenario, right? The controller given by theta RL performs poorly, right? So this is how I would reason through a learning algorithm, right? So suppose all of these things were true. Suppose that, again, corresponding to the 3 steps in the previous slide, suppose the helicopter simulator was accurate, and suppose the learning algorithm correctly minimizes the cost function, and suppose J of theta is a good cost function, right? If all of these things were true, then the learned parameters should fly well on the actual helicopter, right? But it doesn't fly well on the helicopter, so one of these 3 things is false, and our job is to figure out is to identify at least one of these 3 statements, 1, 2, or 3, that is false, because that lets you sink your teeth into something to work on, right? And I think to make an analogy to more conventional software debugging, if you have a big complicated program and for some reason your program crashes, like a code dumps or whatever, if you can isolate this big complicated program into one component that crashes, then you can focus your attention on that component that you know crashes for some reason and try to find a bug there, right? And so instead of trying to look over a huge code base, if you could do binary search or try to isolate the problem in a smaller part of your code base, then you could focus your debugging efforts on that part of your code base, try to figure out why it crashes, and then fix that first. And after you fix that, it might still crash, then there might be a second problem to work on, but at least you know that trying to fix the first bug seems like a worthwhile thing to do, right? So what we're going to do is come up with sorry about the gradient design, come up with a set of diagnostics to isolate the problem to one of these 3 components, okay? So the first step is let's look at how well the algorithm flies in simulation, right? So what I said just now was you ran the algorithm and it resulted in a set of parameters that doesn't do well on your actual helicopter. So the first thing I would do is just check how well does this thing even do in simulation, right? And there are 2 possible cases. If it flies well in simulation but doesn't do well in real life, then it means something's wrong with the simulator, right? It means it's actually worth working on the simulator. Because, if it's already working well in the simulator, I mean, what else could you expect the reinforcement learning algorithm to do, right? You told the reinforcement learning algorithm to go and fly well in the simulator because it's just trained in simulation. It's already doing well in the simulator, so there's not much to improve on there, right? Or at least it's hard to improve on that. But if you found if your learning algorithm does well in the simulator but not in real life, then this means that the simulator isn't matching real life well. And so that's strong evidence, that's strong grounds for you to spend some time to improve your simulator. Yeah?
Is it ever the case that the helicopter flies badly in the simulator but well in real life?
Oh, yeah. Right. Is it just repeat for the camera? Is it ever the case that it flies badly in simulator but well in real life? I wish that happened. No, actually, very rarely. I think if that happens, I would still work on improving the simulator. So there's actually one scenario where that happens. It turns out that when we train a helicopter in the simulator, or really any robot in the simulator, we often add a lot of noise to the simulator because one of the lessons we've learned is that if your simulator is noisy, because simulators are always wrong, right? Any digital simulation is only an approximation of the real world. So we tend to add a lot of noise to all of our simulators because we think that if a learning algorithm is robust to all this noise you've thrown at it in simulation, then whatever noise the real world throws at it, it has a bigger chance of being robust too as well. And so we tend to throw a lot of noise into our simulators. And so one case where that does happen is when we find we threw too much noise at it in simulation. And then that might be a sign we should dial back the noise a bit. Yeah. All right, cool. Yeah, right. So this first diagnostic tells you should work on improving simulation. But just, I think if there's a big mismatch between simulation performance and real world performance, that's a good sign that, that you should improve the simulation. Second, this is actually very similar to the diagnostic we use on the SPAM, Bayesian logistic regression SVM example. So what we're going to do is we're going to measure this equation. And this is very similar to our previous equation, which is take the cost function, similar to the previous example. Take the cost function j that reinforcement learning is told to minimize, right? J of theta was a squared error, right? So take the cost function that reinforcement learning was told to minimize and see if the human achieves better squared error than the reinforcement learning algorithm, right? And just see, the human flies better, so let's measure the human performance on this squared error cost function and see which one does better. So there are two cases. That equation will be either less than or it'll be greater than or equal to, right? So less or greater than equal to. So case one is theta human is less than, j of theta human is less than j of theta RL. That would be this case. Then that tells you that the problem is with the reinforcement learning algorithm, right? That somehow the human achieves a lower squared error, and so the learning algorithm is not finding the best possible squared error. That there's some other controller, as evidenced by whatever the human is doing, that actually achieves a lower cost function, right? So in this case, we think the learning algorithm, our reinforcement learning algorithm is not doing a good job minimizing that, and we'll work on the reinforcement learning algorithm. The other case would be if the sign of the inequality is the other way around, right? Now, in this case, you can infer that the problem is in the cost function, because what happens here is the human is flying better than your reinforcement learning algorithm, but the human is achieving what looks like a worse cost than your reinforcement learning algorithm. So what this tells you is that minimizing j of theta does not correspond to flying well. Right? Your learning algorithm achieves a better value for j of theta. J of theta RL is actually smaller than whatever human is doing. So the reinforcement learning algorithm, as far as it knows, is doing a great job because it's finding a value of theta where j of theta is really, really small. But in this last case, you know that finding such a small value of j of theta doesn't correspond to flying well because a human doesn't achieve such a good value in the cost function, but the helicopter actually just looks better or is flying in a more satisfactory way. And that tells you that the squared error cost function is not the right cost function for what flying accurately means, right? And so through this set of diagnostics, you could decide which one of these three things, improving the simulator, improving the RL algorithm, reinforcement learning algorithm, or improving the cost function is the thing you should work on. Right? And what happens and actually in this particular project, and what often happens in machine learning applications is you run the set of diagnostics, and this actually happened when we're working on this helicopter. We run the set of diagnostics, and then 1 week we would say, yep, simulator's got a problem, let's work on that. And then we'd improve the simulator, and after a couple of weeks of work, we'd run these diagnostics and say, oh, it looks like the simulator is not good enough, and maybe there's a problem in the RL algorithm. Then we work on that, improve that, and after a while, we'll say, oh, looks like that's also good enough, and the problem is in the cost function. And sometimes the location of the most acute problem shifts, right? After you've cleared out one set of problems, it might be the case that now the bottleneck is the simulator, right? And so I often use this workflow to constantly drive prioritization for what to work on next, right? And to answer the question just now about how do you find a new cost function, it turns out finding a new cost function is actually not that easy. So actually one of my former PhD students, Adam Coates, through this type of process realized that finding a good cost function is actually really difficult Because if you want a helicopter to fly a maneuver, like fly at speed and then make a bank turn, right? Like how do you mathematically define what is an accurate bank turn? It's actually really difficult to write down an equation to specify what is a good way for how to fly like that and then do a turn. It's just, how do you specify what is a good turn? So he wound up writing a research paper, one of the best application paper in modern ICML, on how to define a good cost function. It's actually pretty complicated, but the reason he did it, and it was a good use of his time, was running diagnostics like these, which gave us confidence that this was actually a worthwhile problem, and that resulted in making real progress in the helicopter in the end. Right? Any questions about this? Cool. Actually, I think all right, anyway, all right, fun helicopter videos. No, let's not show this, it's fine. You guys saw some of these earlier. All right, so, let me see how I am on time. Yeah, all right, let's go through this. So, in addition to these specific diagnoses of bias versus variance and optimization algorithm versus optimization objective. Sorry, and when we do RL, I want to just go through that example one more time. So you see everything we just saw again after you've learned about reinforcement learning later in this quarter. Okay. Now, in addition to these type of diagnostics, how to debug learning algorithms, there's one other set of tools you find very useful, which is error analysis tools, which lets you figure out, which is another way for you to figure out what's working, what's not working, or really what's not working in the learning algorithm. So let's go through a motivating example. So let's say you're building a like a security system. So when someone walks in front of a door, you unlock the door knob based on whether or not that person is authorized to enter that place. And so let's say that so there are a lot of machine learning applications where it's not just one learning algorithm, right? But instead you have a pipeline of stringing together many different steps. So how do you actually build a face recognition algorithm to decide if someone approaching your front door is authorized to unlock the door, right? Well, here's something you could do, which is you start with the camera image like this, and then you could do pre-processing to remove the background. So all that complicated color background, let's get rid of that. And it turns out that when you have a camera against a static background, right, you could actually do this with a little bit of noise, but relatively easy. Because if you have a fixed camera that's just like mounted, on your door frame, it always sees the same background. And so you can just look at what pixels have changed and just keep the pixels that have changed compared to, right, because, this camera always sees that gray background and that brown bench in the back. And so you just look at what pixels have changed a lot and that's background removal, right? So this is actually feasible by just looking at what pixels have changed and keeping the pixels that have changed relative to the background. And so after getting rid of the background, you could run a face detection algorithm, and then after detecting the face, it turns out I've actually worked a bunch on face detection and built a bunch of face recognition systems. It turns out that for some of the leading face recognition systems, it depends on the details, but some of them, it turns out that the appearance of the eyes is a very important cue for recognizing people. This is why if you cover your eyes, you actually have a much harder time recognizing people, as eyes are very distinctive of people. You can segment out the eyes, segment out the nose, another thing you segment out the mouth. It's Halloween. And then feed these features into some other algorithm, say literacy regression, that then finally outputs a label that says, is this the person, right? That you're authorized to open the door for. So in many learning algorithms, you have a complicated pipeline like this of different components that have to be strung together. And if you read the newspaper articles about, or if you read research papers in machine learning, often the research papers will say, oh, we built a machine translation system. We've trained it on a gazillion, sentences found on the internet, and it does great in a pure end-to-end system. So that's like one learning algorithm that sucks in an input, like suck in an English sentence and spit out a French sentence or something, right? So that's like one learning algorithm. It turns out that for a lot of practical applications, if you don't have a gazillion examples, you end up designing much more complex machine learning pipelines like this, where it's not just one monolithic learning algorithm, but instead there are many different smaller components. And I think I think that I think that having a lot of data is great, right? I love having more data, but big data has also been a little bit overhyped. And there are a lot of things you could do with small data sets as well. And in the teams I work with, we find that if you have a relatively small data set, often you can still get great results. I don't know, my teams often get great results, like 100 images, 100 training examples or something. But when you have small data, it often takes more insightful design of machine learning pipelines like this, right? Now, when you have a machine learning pipeline like this, the things you want to do, one thing you want to do is, so you build a pipeline like this and it doesn't work, right? It's this common workflow. You build something, doesn't work, so you want to debug it. So in order to decide which part of the pipeline to work on, is very useful if you can look at the error of your system and try to attribute the error to the different components so that you can decide which component to work on next, right? And there's actually I'll tell you a true story. Remember the pre-process background removal step, right? Just getting rid of the background. It turns out that there are a lot of details of how to do background removal. For example, the simple way to do it is to look at every pixel and just see which pixels have changed. But it turns out that if there's a tree in the background that waves a little bit because the wind moves the tree and blows the leaves and branches around a little bit, then sometimes the background pixels do change a little bit. And so they're actually really complicated background removal algorithms that try to model basically the trees and the bushes moving around a little bit in the background. So you know that even though the pixels that the tree moves around is part of the background, you should still get rid of it. So background removal, there's simple versions where you just look at each pixel and see how much has changed, and they're incredibly complicated versions. So I actually know someone that was trying to work on a problem like this, and they decided to improve their background removal algorithm. And they actually, this person actually literally wrote a PhD thesis on background removal. And so I'm glad he got a PhD. But when I look at the problem he was actually trying to solve, I don't think it actually moved the needle, right? So this is one of the nice things about academia, because so long as you can still publish a paper, and it was technically innovative. It was actually very good technical work. But if it goes to publish a paper, great, do that. But if it goes to build a better face recognition system, then I would carefully ask which component should you actually spend your time to work on, right? So here's what you can do with error analysis, which is, say your overall system has 85% accuracy. Here's what I would do. I would go in and in your dev set, in your development set, the whole cross validation set, right? Go in and for every one of your examples in the dev set, I would plug in the ground truth for the background, meaning that rather than using some approximate heuristic algorithm for roughly cleaning out the background, which may or may not work that well, I would just use Photoshop. And for every example in the dev set, I would give it the perfect background removal, right? So imagine if instead of some noisy algorithm trying to remove the background, this step of the algorithm just had perfect performance, right? And then you could give it perfect performance on your dev set, on your test set, just by using Photoshop to just tell it, this is a background, this is a foreground, right? And let's say that when you plug in this perfect background removal, the accuracy improves to 85.1%. And then you can keep on going from left to right in this pipeline, which is now, instead of using some learning algorithm to do face detection, let's just go in and for the test set, modify, kind of have the face detection algorithm cheat, right? Have it just memorize the right location for the face in the test set and just give it a perfect result in the test set. So when I shade in these things, that means I'm giving it the perfect result, right? So let's just go in and on the test set, give it the perfect face detection for every single example, and then look at the final output and see how that changes the accuracy of the final output, right? And then same for these components, eye segmentation, nose segmentation, mouth segmentation, and you do these one at a time. And then finally, for logistic regression, if you give it the perfect output, your accuracy should be 100%, right? So now what you can do is look at the sequence of steps and see which one gave you the biggest gain. And it looks like, in this example, it looks like when you gave it perfect face detection, the accuracy improved from 85.1 to 91%, so roughly a 6% improvement. And that tells you that if only you can improve your face detection algorithm, maybe your overall system could get better by as much as 6%. So this gives you faith that maybe it's worth improving on your face detection component. And in contrast, this tells you that even if you had perfect background removal, it's only 0.1% better. So maybe don't spend too much time on that. And it looks like that when you gave it perfect eye segmentation, it went up another 4%. So maybe that's another good project to prioritize, right? And if you're in a team, one common structure would be to do this type of analysis and then have some people work on face detection, some people work on eye segmentation. You could usually do a few things in parallel if you have a large engineering team. But at least this should give you a sense of the relative prioritization of the different things. This question?
Could you do this cumulatively, or would you make the eye segmentation perfect and then kind of go back and now the eye segmentation is not perfect anymore and now we fix the nose segmentation, or do you kind of add property to the previous?
Yeah, right. So do you just cumulatively, such as give it perfect eye segmentation, then add on top perfect nose segmentation, or do you give it perfect eye segmentation, and then take that away, and then give it perfect nose segmentation? The way I presented it here is done cumulatively, and it turns out that, let's see, if you give it, once you give it perfect face, once you give it, perfect things in the later stages, maybe the earlier stages doesn't matter that much anymore. So that's one pattern. But it turns out that you could do it either way, right? For the eyes, nose, mouth, you could do it cumulatively or one at a time, and you'll probably get relatively similar results. No guarantee. You might get different results in terms of conclusions, but I think to the extent that you are wondering if doing it cumulatively versus non-cumulatively might give you different results, I would just do it both ways, and I think these error analysis is not a hard mathematical rule, if that makes sense. It's not that you do this and then there's a formula that tells you, okay, work on face detection, right? I think that this should be married with judgments on, how hard do you think it is to improve face detection versus eye segmentation, right? But this at least gives you a sense of it gives you a sense of prioritization. And it's worth doing this in multiple ways if you think that if you are concerned about discrepancy between the cumulative and non-cumulative versions. All right. So whenever you have a complex machine learning pipeline, this type of error analysis helps you break down the error to attribute the error to different components, which lets you focus your attention on what to work on.
So if you, for example, do face detection perfectly and the accuracy actually drops, what that indicates?
Oh, right, yeah. If you do face detection accuracy and then your error drops, what does that indicate? It's not impossible for that to happen. It would be quite rare. I would, so at a high level, what I would do is go in and try to figure out what's going on, actually. I wouldn't ignore that. So this is another thing I see. Sometimes a team discovers a weird phenomenon like that, and they just ignore it and move on. I wouldn't do that. It's actually gold. Whenever you find one of these weird things, I wouldn't gloss over it or ignore it. I would go in and figure out what's going on. Does this make sense? It's like debugging software. If you're trying to debug a piece of software, and if whenever you move your mouse over, some button, some random pixel color changes, you go, that's weird. And then some people just ignore it. It's like, oh, well, the user won't see this. But so, let's go figure it out, right? Yeah. So what you're saying is quite rare, but not impossible. But I don't have an easy solution for how to figure out what's going on, but I would want to figure out what's going on. All right, so one last thing before we break. So error analysis helps figure out the difference between where you are now, 85% overall system accuracy, and 100%, right? So it tries to explain the difference between where you are and perfect performance. There's a different type of analysis called ablative analysis, which figures out the difference between where you are and something much worse. So here's what I mean. So let's say that you built let's say you build a good anti-spam classifier by adding lots of clever features to literacy regression, right? So spelling correction, because spammers try to misspell words to mess up the tokenizer, to make words look, spammy words not look like spammy words. Sender host features, what machine did the email come from? Email header features, you could have a parser from NLP, parse the text, use JavaScript parsers to understand, right? Or even go and fetch the web pages that the email refers to and parse that. And the question is, how well did each of these components really help? And it turns out, if you're writing a research paper, sometimes you write a research paper and say, hey, look, I built a great spam classifier, and that's okay. That's like a nice result to have. But if you can explain to your reader, either in a research paper or in a class project report, like a term project, what actually made a difference, that conveys a lot of insight as well. So, say simple literacy regression, with all these clever features, got 94% performance. And with all of your addition of all these clever features, you got 99% accuracy. So in ablative analysis, what you would do is remove the components one at a time to see how it breaks, right? So just now, we were adding to the system by making components perfect with error analysis to see how it improves. Here, we're going to remove things one at a time. Oh, did not mean to remove that. Let's figure out what's going on with PowerPoint. All right, remove things one at a time to see how it breaks. So let's see, remove spelling correction. And as a set of features, the error goes down like that. Then let's remove the sender host features, remove the email header features, and so on, until when you remove all of these features, you end up there. And again, you could do this cumulatively, or remove one and put it back, remove one and put it back. Or you could do it both ways and see if they give you slightly different insights. And so the conclusion from this particular analysis is that the biggest gap is from the text parser features, because when you remove that, the error, the accuracy went down by 4%. And so, this is strong evidence. If you want to publish a paper, you could say, right, text parser features significantly improves spam filter accuracy, and then that level of insight. And then if you're working on a spam filter for many years, right, there are really important applications where sometimes the same team will work on for many years. So this type of error analysis gives you intuition about what's important and what's not, and helps you decide to maybe even double down on text parser features, or maybe if the sender host features is too computationally expensive to compute, tells you maybe you can just get rid of that and without too much harm. And also, if you're publishing a paper or sending a report, this gives much more insight to your report. Okay? All right. So that's it for error analysis and ablative analysis. I hope this was useful for your class projects as well. I'll take one last question.
How would you choose the order in which to remove features?
Oh, yeah. How would you choose the order in which you remove? No systematic way. If you can have a systematic way, you do that. The other way, the non-cumulative, where they remove one, put it back, remove one, put it back. So either way works. All right, let's break. And problem set 2 is due tonight. Friendly reminder, and problem set 3 will be posted in the next several tens of minutes. Okay, thanks everyone.